Okay, now I'm going to come back to the helium flash slides. That's to clarify where I wasn't clear last night because I wasn't appropriately prepared on that topic. So the quiz, number one, approximately how long is a star in the main sequence? Now let's go with ones we can rule out. What can we easily rule out?
F you can rule out.
Why can I rule out F?
Because it doesn't spend so life on it.
Okay, because it just doesn't. I was thinking the top two. Because how long it spends in the main sequence depends on the star. And so we can rule those out. And then we just have what percentage of its life. And the percentage is a rough percentage. It's going to vary a little bit by star. But Alden, what is it?
90% of its life.
90% of its life.
And how many stars are in the main sequence right now?
About 90% of them for the same reason. Now, that means it has 10% of its life left. What do you suppose it's doing for that 10%?
Dying.
It's dying. Well, good. It is dying. For that 10%, it's pretty much fusing helium in its core. That essentially second main sequence. The amount of time that it's not doing one of those two is a very small percentage of its time. The hydrogen fusion is what's going on for the main sequence part. Now, the second one is just a little tricky, which, of course, it's always unfortunate to be tricky. What's going on in the core of a star? I made core bold so you wouldn't think of, oh, it's got the shells doing this. When it's in the on the red giant branch. Now, I said it's kind of tricky. So this one here is probably going to be one with a lower percentage score on. Are there any things that you can rule out just right off the top of your head?
The core expanding.
Okay. Core expanding, that's got to be wrong. That pretty much never happens, except for when it blows up. There's another, well.
Helium to carbon.
Okay. Helium to carbon isn't incorrect, although I'd be willing to bet there's a lot of people who answered that one. Because that's what's going to happen after the red giant branch when it reaches its second stable portion. And so a lot of people, I think that's the problem. They tend to think, oh, it's no longer fusing hydrogen, so it must be helium. But the red giant branch is when it has the hydrogen shell, but it hasn't started fusing helium in the core yet. This one here never, ever, ever happens because beryllium is unstable. Well, the beryllium that you would form is unstable. There are stable isotopes of beryllium, but it's beryllium-7, not beryllium-8. The core fusing hydrogen to helium, that's what occurred until it went on to the red giant branch. Contracting is actually the answer. Okay, now the last one. Let's draw as careful as we can. Vertical line. We're going to pretend that's vertical. No, that's more vertical. Horizontal line.
That is not right. That's not right.
Better.
You kind of went the same distance below.
No, I'm a little below, but not the same distance. I'm going to leave it there. What do we have on each axis? What's on the bottom axis? Temperature. Which side is hot? So this side is hot. This side is cool. I saw a number of people doing the O, B, A, F, G, K, M, L, T, right? Because they knew what they were doing. Me, you can see I'm not an artist. What's on the vertical axis?
Space.
Luminosity.
Relative.
And so we're going to have here's like one solar luminosity. So my units are going to, oh, that's an L. You can tell. L sun. I tried to put a dot in the center. I really, really tried. Dang it. I'm doing well. There, dot in the center. So there's one. We have 0.1, 0.01, 10, 100. It's logarithmic. That's why I put the number so we can see that it's logarithmic. Because the difference, the spacing between these is equal, but the difference is multiplied by 10. So that makes it logarithmic. Okay, and of course we have the main sequence is somewhere in here. And then we have our regions of like and down here's white dwarfs. So there's my HR diagram. Then we had to put the life cycle going from a stellar nebula to a main sequence star. Now let's start with the easy things. I saw this was a big problem for students. What's the rough temperature of that stellar nebula before the shockwave hits it? Cold. Something like 10 kelvins, 10 to 15 kelvins. I initially said 3 and I was wrong, but so where is cold? We have hot and cool. Where is cold? It's over to the right. In fact, you know what I'm going to do? I'm going to take this thing and I'm going to shrink it and move it so I can go further to the right. So we're going to start way out here because it starts really, really cold. And how much light is it giving off when you just have the gas? Virtually none. So it starts there. A shock wave hits that stellar nebula, the molecular cloud, if you will, and it starts compressing and gravity takes over and things start falling in. What happens to the speed of things as they fall in toward the center? The speed goes? Faster. And that means the temperature goes up. So it's getting hotter. And as it's getting hotter, what does that tell you about the luminosity? It's going to be getting off more. So it's going to be going up for more luminous and left for hotter. So it's going to be coming like this. Then it comes in here and goes something like that.
I definitely got this wrong.
So that's what the birth line is like for a star that's roughly the mass of our sun. Now, we didn't have the death line, but we could have done the death line. It would have, come up here, gone through the giant, come down, come back and around. I did the hand waving before class. Then I had a question here about how long it takes. How long does it take for a star like the sun to be born? These were all separated by a factor of 100, so, it's not that big of a jump.
1 billion years?
Nope. It's the one just above that.
10.
About 10 million years for a star the size of the sun to be born. How long will the star the size of the sun be on the main sequence? That's about 10 billion years. So about 1,000th of his lifetime, or it takes about 1,000th of its lifetime for the formation portion. Okay, any questions about the quiz? You learn from it? So even if it doesn't raise your grade, if you learn from it, it's a success. This is the slide that I had last class period that I kind of like, I didn't really prepare on that. Finally, Google Drive has me up to date there. And so it was this here that I fumbled on. So the next slide gives us the lowdown. And what is that lowdown? It's that stars that are less than half a solar mass, they actually reach electron degeneracy while they're still fusing hydrogen. And that electron degeneracy while they're fusing hydrogen essentially stops the fusion of hydrogen. So they're burning along and also the fusion just goes out. And then they collapse and they're done. So stars less than half a solar mass never will have a giant stage because of the electron degeneracy. That's the part that I fumbled last night. If it's between a half and 2 solar masses, last night I said 3 solar masses, so I wasn't far off, but you know what? You want to be more right than more wrong. So a half to 2 solar masses, it will reach the electron degeneracy in the core after it's finished fusing hydrogen, but before it started fusing helium. And then when helium fusion starts, that's when you have the big eruption, which I said is very brief. Up here we actually have the time. It only lasts a few hours, not days, not years, few hours. So it's a very brief major explosion in the entire core, making the core expand some, removing the degeneracy, and then it starts functioning just as a stable star nucleus, except for now it's fusing helium into carbon via the triple alpha process. If it's more than 2 solar masses, it won't reach degeneracy before it starts fusing helium. In that case, it just starts fusing helium, just ramps up. So it doesn't have the helium flash. So you have basically 2 numbers, no helium fusion at all below a half a solar mass because it reaches electron degeneracy while it's still fusing hydrogen. Between a half solar mass and 2 solar masses, you're going to have the helium flash and then have your helium fusion in the core. More than 2 solar masses, it will just smoothly transition to helium fusion in the core rather than having a big flash when it starts. So I want to make sure I got that straight rather than leaving you, hey, he was confused and so am I. Okay, so our first clicker question. Will the sun have a helium flash? Your options A through F are no for different reasons, and option G is yes. I'm a little worried that no one's answered yet. Okay. Somebody's answered. I just worry that like the technology, something's gone wrong. But Max has answered. I should figure out what my answer is. Okay, we're all in. We have a range here, 0, 5, 1, 0, 1, 3, 1. Now I'm going to give you one piece of data and have you talk to people before Yeri explains it to you. And that is the mass of the sun is equal to 1 solar mass. Yes. That's in case that didn't, that's the important factor here. So talk to your neighbors about the answers and see if we can come to a better conclusion.
I don't remember.
All right, go ahead and answer again. We are definitely doing better. All right. Since we're definitely doing better and only one went up, you know what the correct answer is? Yeri? Yari.
G. That's fine.
B is in boy.
G.
G is in good.
Yes. Because from what you said, it was from 0.5 to 2, and you're saying that the sun is 1 solar mass. So it's in that range. I thought.
No, you were absolutely right. I'm writing down the full answer. You were absolutely right.
Okay.
Two to, I don't know. Let's go to 150. Okay, 0.08 is the minimum mass for a star, so that's why I put that as my minimum. Up to 0.5 solar masses, you reach degeneracy in the hydrogen before you're done fusing that, and it just kills the hydrogen fusion. And so it doesn't become a giant of any type, it doesn't fuse helium, it's just done when that occurs. Between a half a solar mass and 2 solar masses, it will finish fusing hydrogen into helium. It will have the shell burn out, and while the shell is burning out, it will reach electron degeneracy in the core. And that reaching electron degeneracy in the core is the key for the helium flash. So when it reaches high enough temperature in the core, it will start fusing helium everywhere and give you the helium flash. And then 2 to 150 solar masses, it won't reach electron degeneracy, and so it will just have the hydrogen shell burning out, and then it will start fusing helium in the core, but no flash. So you were absolutely right. I wanted to make sure I got the whole thing written out. You had the right answer. I had to put the 2 wrong answers. All right. Here is looking at all of the calculated times for the stages of our sun from birth to death. And I know this looks like Gabriel's trumpet or something, but what you have there is the horizontal axis is time, the vertical axis is how big it is, and then of course the color is supposed to represent what it would look like in the sky. So you have the first region is gray. Why gray? Because it's enshrouded with dust and not much light gets out. That's when you have the protostar forming. And that you see it says about 20 million years. On our quiz, I had 10 million. Your next step was 100 million. Obviously, 10 million is much closer to 20 million than 100 million is. So it says about 20 million years for it to go through that protostar stage. Then it turns the key to become a star, which means it starts fusing hydrogen to helium. And when that occurs, you have that nice long main sequence period of about 10 billion years. When the core runs low, then you're going to have a shell burn out. You go in the red giant stage, and so that you see is an increase in size, the flaring of the bell, if you will. And that stage lasts for about 1 billion years. So 10 billion years on the main sequence, 1 billion years is a red giant. Notice all the times after that are smaller by a reasonable fraction. You have 100 million years as a yellow giant. What's going on in the yellow giant stage? That's where you have helium fusing into carbon via the triple alpha process in the core. So that's another stable branch. Now, we'll see a picture later on that makes it look like, actually I think it's 2 slides from here, that makes it look like the shells stop burning there, but that's not true. The shells will keep going on even when you're in that stable period. But when you finish the fusion of helium into carbon, which is just 1/10 the time for a star the size of our sun, then, well, you're pretty much done. You've got that mirror variable. Do you remember the mirror variables from last night? They're stars that are dying that have a variable getting brighter or dimmer with the period that's on the order of a year. Very long period for them to oscillate in brightness. And so we'll spend about 10,000 years How much is 10,000 compared to 10 billion? It's a negligible amount. So, 0.0 whatever percent. And we can do the math real quick, but I don't care to. And then it'll be all done. The planetary nebula, that's remnants, right? There's no longer fusion when you have the planetary nebula. And that's the 10,000 years. And finally, white dwarf. White dwarf is tiny. What does that blue color represent? It means that it's, was it muy caliente? No? Mucho? I was trying to learn Spanish and then I got bogged down trying to grade instead. So it's really hot there, but it's also really small. So it cools very slowly. So that's basically the life cycle of our sun. Here it is drawn out on an HR diagram. So you see the gray line there is the line that you were to reproduce on the quiz. It didn't start out here like I tried to make mine start. Excellent work. But you have the protostar coming to the main sequence. The yellow there is when it's on the main sequence. Then you go and you have your red giant stage. You have your helium flash up here, the yellow giant stage. The mirror variable there is in red. And notice the times are shown. So it's 11.1 billion years when it is there at the bottom of the yellow giant stage. And it's 11.11 billion years when it's done with the mirror variable, right? Compared to its lifetime, we're talking a small fraction. And then it's 11.11001 billion years to get to the white dwarf stage. So it goes really quickly, comparatively, through the last stages. But to me, it tells an interesting story to look at the entire picture here and see what's going to go on with the star as it's dying. This is an interesting, albeit a little confusing, explanation of why red giants expand. Remember I said you have the shell burning out and that causes it to expand. The actual process of why it expands is kind of curious. It actually forms little carbon flakes. Like when you burn something in fire, you have soot. You put your hand over you wouldn't want to put your hand over a badly burning flame, but put like a piece of metal in it, it will collect soot. That's essentially what it's talking about here. Building up little carbon flakes in the atmosphere of the sun. But then those carbon flakes are pushed out by what we call radiation pressure. Light actually will put a force on things. When light hits something, it puts a force on it. And so that radiation pressure pushes that out. And that's actually the process they believe on what causes the red giants to expand when you have that shell burning out. And that material then gets blown off to give us the pretty planetary nebula. I believe everyone should agree that planetary nebulae are pretty, right? You're with me? Thank you.
Aren't those heavily edited?
No, actually. These are true color. Here's another picture of a planetary nebula. What do you notice distinctly different between this one and the one we just saw? The biggest thing that I notice is, you've got the all-seeing eye there in the center. I don't know if it's Sauron or what, but it's not symmetric like the previous one was. There's clearly some asymmetry to this. It's not spherically symmetric. So it's called the hourglass nebula because it looks kind of like an hourglass. But you have all of that gas that's lit up, used to be part of the star. It was pushed off in the giant stage as it was blown away by that radiation pressure, and then a shock wave goes through and makes it light up. So these planetary nebulae are very interesting to look at because, they're pretty. This, of course, is the one we just looked at before. At the center of the planetary nebula, we have the remnant. What do we call the remnant of the core? The white dwarf. So that's the white dwarf there that I circled in the center. And its temperature is around 25,000 kelvins. Now, if we look back at the HR diagram, you see that the peak temperature it showed here was around 100,000 kelvins. And it shows it as a white dwarf when it gets down here to somewhere around 65-ish thousand kelvins. So the 25,000 kelvins, that's actually coming right here. That's on the low, well, it's an intermediate temperature at best for the white dwarfs. They get much hotter than that. And like I said before, it will eventually become a black dwarf, but it takes a very long time to cool because it has a small surface area. Thus, it can't radiate very much. Remember that radiation luminosity was equal to sigma epsilon area temperature to the fourth equals sigma epsilon 4 pi radius squared times temperature to the fourth. The radius of a white dwarf is about 50 kilometers or somewhere in that ballpark. Because that's very small compared to the radius of the sun, the amount that it can radiate is much smaller than what the sun can radiate because of the smaller surface area. Now the novae that I talked about. Novae is plural of nova. To have a nova, you have to have a white dwarf that has a companion star that's dying. So this picture shows a white dwarf. You can't see it because it has a companion that's in the red giant stage. In that red giant stage, it's blowing off a lot of gas. But if it has the companion, the white dwarf just says, come on over, I've got room for more. The gas that's being expelled is still primarily hydrogen. And we have to talk just a little bit about the Roche surface again. The Roche surface, I said the Roche surface again, we talked about a little bit when we talked about things falling into Jupiter and getting torn apart and making rings. Well, inside of what's called the Roche lobe, any mass that's in there can't escape. It's gravitationally bound to the star. And so mathematically, we can calculate what the radius is for the Roche lobe of a star by itself. Now, if you have two stars, both stars are interacting, so it gets a little more complicated to calculate where the Roche lobe is. But essentially, what you find is, for the two stars, you have something that looks kind of like a figure eight. So anything inside of one of those lobes belongs to the star that is inside of that. But there's a place where those two touch. And where those touch, gas could go from one star to the other star. And so that's the key for a nova. You have that red giant that is pushing off mass. It gets to that, I think it's called the inner Lagrangian point. I may be wrong, though. Gets to that point and transfers and becomes part of the mass of the white dwarf. So then as it comes in, of course, it does have to conserve angular momentum, so it's going to spin around. But because of collisions, it'll lose energy and fall in. And over time, you'll build more and more pressure on the surface of that white dwarf. More and more pressure. The temperature is already hot. It's going to build up hotter and hotter temperature because of the infall until you reach a high enough temperature. How hot does it have to be to fuse hydrogen to helium?
Hot.
That's a reasonable answer, but it's not a number. We had a graphic last night that said 10 million kelvins. I'll have another one in just a moment, I think, that says 5 million kelvins. But it has to be in the millions of kelvins. When you get to a high enough temperature and pressure on the surface, then the surface just erupts. So you have an explosion. There's the picture of the explosion on the surface. A big flash of light. And it will stay lit up for a short amount of time, a few months maybe, and then it will fade away. Now, what happens to the white dwarf during this process? Nothing. It's basically just an inert lump. It says, yeah, something happened on my surface. Hey, I'm more massive. I got more helium now. Life is still good. And so I can just do this over and over, hence the term recurrent nova. Because a nova is caused by mass coming from one star over to the white dwarf, in most situations, the nova is going to occur over and over and over again. Each time, you're just more mass for the white dwarf. So the white dwarf gains mass because it's pulling off of its neighbor. Here's actual photographs of a nova. So this is right after the nova occurs, and then a little bit later, you have a ring out there, a shock wave going out. So as this goes on, the mass can continue until we reach that Chandrasekhar limit, the 1.4 solar masses. As it builds more mass, the temperature shoots up dramatically. And when you get to that 1.4 solar masses, the temperature is high enough and the pressure is high enough that you actually will start fusing the oxygen and carbon that you have in the white dwarf. And when that occurs, you're going to release a huge amount of energy, and it goes kablooey, blows up, and you're going to have nothing left except for a cloud of gas. So this picture here shows the explosion and then nothing left but a cloud of gas. This is the companion, as in not the star that blew up, but the other one that was near it, that was giving it mass. Right, so don't get confused about what's that companion. Is that the core? No, it's the other one. So this is called a Type 1a supernova. Type 1a supernova is a white dwarf that reached the Chandrasekhar limit and exploded and left behind just a cloud of gas. Now this is very reproducible. Because what's the mass when you have a Type 1a supernova?
1.4.
It's always 1.4 solar masses. What elements was it made out of? Yeah, primarily carbon and oxygen, and some helium. But it's pretty much exactly the same elements every time. So you have the same elements, you have the same mass. It's going to explode the same way. So these are very reproducible, which makes them useful in astronomy. That means they're always going to have the same brightness. So if we see a Type 1a supernova, we can say, oh, it must have been this, actually same brightness, I should have said the luminosity. It had this luminosity, but measured from Earth, it has this brightness. If I measure its brightness from Earth and I know its luminosity, what can I calculate from those two numbers? I can calculate its distance. So you can calculate the distance using the Type 1a supernova. So we learned last class period about the variables. The Cepheid variables, there was a luminosity relationship with the period. So if you can measure the period, you know the luminosity. You measure its brightness from Earth, and you can determine its distance. The R-Leary variables, they just didn't have much variation in their luminosity. So it's still useful as what we call a standard candle. We know how bright it is. That's what standard candle means. Because it's a R-Leary, and they're all about the same brightness. Or same luminosity, so if we measure its brightness, we know its luminosity, we can calculate the distance. So here's what the luminosity curve looks like for a Type 1a supernova. Notice it reaches its peak here. The zero there is the time when it reaches its peak. But if you look at those, that's 100 days. So that's maybe 10 days after the nova occurs, it reaches its peak luminosity. And then the luminosity starts to decay over like a year. It gets much dimmer though. Notice this is a logarithmic scale. So going from here to here, it's dropped by a factor of 10 in its luminosity. Down to here, it's dropped by a factor of 100. So it basically has dropped by a factor of 100 from its brightest luminosity in a year. And like I said, Type 1As are very reproducible because it's the same elements and the same mass. So another question about our sun and its future. What end stages, so this is multiple answer, put in all the correct answers and hit enter. What end stages will our sun experience? Okay, everyone's answered. We had 4, 4, 1. Believe it or not, I can't read the next one, but I can tell that it's probably 8, 11, and 3. All right, Jessica, name the one you have the most confidence that our son will have and why you believe that to be true.
I put E.
Well, white dwarf?
Yeah.
And why?
They're like dead stars.
They're like what?
They're dead stars.
Okay, they're dead stars. They're dead stars with a maximum mass of what? There's a maximum mass for white dwarf. What's that maximum mass? Somebody else want to help?
I would, but I don't know.
Appreciate the eyes. The maximum mass for a white dwarf is 1.4 solar masses. So a star that has a mass less than 1.4 solar masses definitely is going to end up as a white dwarf. Is our sun less than 1.4 solar masses? Yes. Now stars during their death, they might lose half of their mass or more. So you could, for instance, have a star that has around 3 solar masses that still ends up as a white dwarf because it sheds so much mass before it gets to its last stage. But our sun being less than 1.4, it definitely is going to be less than that. So our sun will definitely be a white dwarf. Okay. Russell, we have one correct answer taken. Your turn. Aside from that one, what else do you believe our sun will go through?
With Ryan.
That's my go-to.
Okay. Why do you say red giant, Russell?
Because that's on the thoughts fusing helium.
And how much mass does it have to have if it's going to become a red giant?
Like, at least.
Okay. Greater than 0.5 solar masses, and it's going to become a red giant. Less than 1.4 solar masses at death, and it's going to be left as a white dwarf. How many people said planetary nebula? 3. I guess I could answer that. I wrote it down. Planetary nebula is a likely stage that our sun will go through, but there's discussion. It may not quite have enough mass to make the shock wave necessary for the planetary nebula. So that one there, I wouldn't put it on a test because it's something that there's not general agreement on. I think most people think that it will have a planetary nebula. The figures I've showed it having a planetary nebula, but there are others that argue, no, it doesn't have quite enough mass. Why won't it have a type 1a supernova? What do you have to have a type 1a supernova?
Ouch.
Well, you have to get up to greater than 1.4 solar masses. So you have to have an increasing mass. And what's the only situation that's allowed a star to grow in mass? It has to have a dying companion. Our sun doesn't have a companion, hence it won't be able to eat its dying companion and have either a nova or a type 1a supernova. These two here require a companion. And what's left? The type 2 supernova. We'll talk about those in just a minute. So any questions about the end stages for the sun? Low mass stars like the sun? You guys confident on this?
No.
Okay. Aldwin, ask me a question then. Something you're not confident about, something that wasn't clear.
Actually, I'm good.
I also have to recognize that even when you're not clear, that doesn't mean you're clear on what you're not clear on. Okay, well, if you guys have questions, you blurt them out. because I want people to understand.
I got questions all the time.
You do. Okay, now moving to massive stars. I was going to stop there if you gave me a good question because, this is starting a new section. Here's the death sequence on an HR diagram. Now notice this is only going from 10 to the 4th to 10 to the 6th solar luminosities. We're way brighter than the sun is right now here. For a very massive star, a 25 solar mass star. And notice this first stage is hydrogen core fusion. What do we normally call the star when it's fusing hydrogen in the core? Main sequence. So that's our main sequence, our Roman numeral 5. Then we have the hydrogen shell. And the hydrogen shell is going to continue all the way out until we get to the end. And so the reason it shows an end is because that's all that's going on for this period of about 500,000 years. So what do we call this stage when it's just the hydrogen shell?
It's just the hydrogen shell.
Yeah. Okay, I would have said red giant, except for it's still in the blue. So it's a blue supergiant. I'm sorry, it tells you the answers. Now I showed you where it tells you the answers. So that's the blue supergiant. It would have been red giant stage if it was a star the size of our sun. The only difference here is because it's so much hotter that it has a different color. Hence, you can't call it a red giant when it's blue. And why is it a supergiant? Well, because it's really big. Right? So let's make it bigger. Call it supergiant. As it goes from here to here, we have helium fusion in the core. Not a very long period of time there. That's 0.7 million years, or roughly 10% of its lifetime on the main sequence. And you see it's just cooling as it goes through there. And then for the last 300 years, it was fusing carbon, neon, oxygen, and silicon. Not very long for those higher fusions. In fact, this table here shows you the times for a 25 solar mass star. So it's going to spend about 7 million years fusing hydrogen to helium, about 700,000 years fusing helium, about 300 years fusing carbon, about 8 months fusing neon, about 3 months fusing oxygen, and all of 1 day fusing silicon into iron. And when it gets to iron, she's done, because iron is the most stable element. You can release energy by fusion up to iron. You can't release energy by fusion from there. So next class period, we'll talk about what happens at the end of a massive star's life.